Science and Engineering from University of Illinois at Urbana-Champaign in 2015 and completed his postdoc at Stanford University in computational biology and AI and Professor Vijay Pandey. At CMU, his group develops foundation models and neural operators for molecular simulations, generative design of molecules and materials, and AI agent for scientific discovery. And today, Professor Barati Farimani is going to talk about learning the language of atoms, generative pre-training transformers for materials and molecules. And let's welcome.
Thank you so much for the invitation. I'm very excited to talk here at the Bakar Institute, and thanks very much for your hospitality. So today I'm going to talk about the efforts that we did from 2018 to now to the state-of-the-art AI methods into the molecules and the world of materials. So as we know, molecular property prediction, especially in the drug discovery, takes a lot of efforts, time, and also is very expensive. So for a molecule to be a drug, it takes like 15 years almost to develop the drug, and it's like also. The discovery of a molecule is like finding a needle in a haystack. The reason is that the chemical space is enormous. So you can make millions of molecules, billions of molecules, and then you only need one, which is really functioning very well in the proteins. Classically, ML in molecular property prediction before the era of deep learning was that people designed descriptors or features, and then they used shallow machine learning techniques such as kernel, Bayesian, ensemble, and then they predicted the properties. But there were a few problems and challenges for this work, because it was not scalable. It needs a lot of data. And it was very difficult actually to build trustable and highly accurate model. So for the molecular representation, as most of you are aware, I mean, we can have a string, which is a smile or selfies that we're aware of. We can have the 2D topology of a molecule, or you can have a 3D geometry of a molecule. You can have different kinds of representation. And learning this representation is really important, because in any kind of learning, you have two parts. One of them is associating representation to the property of interest, and another part is learning the representation itself, which with the deep neural networks, actually both of them simultaneously are happening. But obviously, the modern challenges that we have in molecular ML is twofold. So the first one is that the magnitude of chemical space is huge. So with a few elements, you can make up to 10 to the power of 30 or 10 to the power of 16 molecules. So if you wanted to find, for example, a drug, a molecule for catalysis, a molecule for example, storage, or any kind of property, you need to search among a huge data set. And you can see that even up to now, we have billions of the molecules in the data sets that we have. For example, DDB17 contains 166 billion molecules. The second problem, which is even more challenging than the first problem, is insufficient and noisy labeled molecular data due to expensive and time-consuming wet lab experiment simulation. So if you wanted to find out a molecule if it is toxic or not toxic, that label is very expensive, right? I mean, you need to send that molecule to the lab to run assay and find out if it is toxic or not. So the label in chemistry is very expensive. That's a very important sentence. Labeling. It's not like images that you have cats and dogs, right? I mean, it's really labeling cat, dog, one thing. So labels in chemistry is expensive, and that's a big problem. And even if you get the labels, like for example, for molecules, those labels are very noisy. So for example, we have TOX21 data set, which is like most of its data, it is very shaky. So it's not like 100% accurate. So what's the solution? What's the solution? Labels are expensive. The chemical expense is huge. The solution is that we have access to molecules without labels. The molecules that are synthesizable, that we can use them, but we don't have their labels. So the question is that can we use these molecules that we don't have the labels, but we have billions of them, millions of them, and learn the representation part without the label and use it to predict, for example, some of the downstream tasks such as toxicity or properties using that. In an essence, can we make use of the large unlabeled data for better ML molecular representation? That's the question. And the answer is yes, by self-supervised learning, which now, I mean, much more popular to talk about the pre-training, right? The P of ChatGPT. So all of us know that ChatGPT was not possible without the P and T, which is the pre-training and transformer. These two are like peas and carrots in making this marvelous things happening for our community and society. So what is SSL or pre-training self-supervised learning? So if I wanted to talk about it in terms of classical battlefield of computer science, in supervised learning, you put labels cat, dog, cat, and then you have a pair of X and Y. But we said in pre-training, we don't have any labels. So you need to make the label. So for example, one strategy that you can use is to get an image, rotate it like 90 degrees, and put a label 90, rotate it more, make another label 180, and create out of the feature space or out of the X data, Y. But this is the Y which is originated from X, right? So this is called self-supervised learning. So this is a beautiful idea because with this thing, I mean, what you can learn, for example, about a cat or dog, you don't care if it is a cat or dog, but what you care is this learning representation of an image. So by doing this exercise, the network, we learn, okay, how, for example, edges look like, how, for example, eyes look like, right? How the mustache of a cat looks like. So these type of things you will learn. So the first thing that we did back in 2020, and we were the first lab to do that, is to bring actually this technique of pre-training to the molecular world. So we have access to significantly large unlabeled data, and you can have an SSL objective, which we can say right now the modern one is pre-training a strategy, right? And then you can train a neural network, and then use those neural network, use those weights that are pre-trained in order to train another network for predicting the downstream tasks. So what is the downstream task? Downstream task is like toxicity prediction, right? So the difference between these two networks is that when you are using this network, the weights already warmed up. So in optimization landscape, if you think about the optimization landscape and you have a local minima here, you are not like in a wanderlust or a kind of lost, I mean, starting with the Javier or, you know, Italian initialization. With this warming up, you go down the basin very closer to the local minima, and you need a few more steps to push it down to learning or fine tuning, right? Downstream. So I wanted just to give you, because I'm teaching deep learning, so I'm saying these things to my students. I thought that it's good to talk about what's our perspective on the optimization landscape and the pre-training. And that is what is actually happening in the ChatGPT for languages. So what we did in this paper, which published in Nature Machine Intelligence in 2022, we considered that you have two smiles of the molecule. What you can do, you can create a molecular graph, then you can augment it. So what does augment mean? It means that you can add a bond, you can remove a bond, you can add an atom, you can remove an atom or subgraph, and create a kind of like augmented molecule. As you can, for example, crop an image and create an augmented image, or you can add a little bit noise for an image. And then you can use a graph neural networks to take it to the latent space. And then with the latent space, you can use the contrastive learning. So using a contrastive loss. So what is contrastive loss? I'll talk about that. I mean, one of the slides is actually moved, so I'll come back to this. So in this talk, actually, I'm going to use these pre-training techniques for contrastive loss that I'm going to talk about. Then I'm going to go and talk about the polymers. Then I'm going to go and talk about MOFs that won the Nobel Prize last week. Congratulations, Professor Yogi. And then I'm going to talk about the textual representations and actually multimodal learning, and then finally some ideas about AI. So let's go back to the what I talked about here about the molecular, which we created. And as I mentioned, like you do the augmentations, there are different ways that you do the augmentation. For example, you do the atom masking, you do the bond deletion, or subgraph removal, and you make a similar instance of that molecule. And then you can create a graph neural networks for embedding that. I don't go over the details of message passing. Most of you are familiar with the graph neural network message passing. But let's talk about what is contrastive loss. So you have a molecule, you augment it, you for example, delete some of the bonds or mask it, you take it to the latent space, it looks like this. You have another molecule, another instance, you augment it in the latent space that looks like that. And these two molecules in the latent space, you a little bit perturb them, right? I mean, so they attract each other. So in the latent space, the cosine similarity should be 1, right? So these two molecules, you should lock them to tell to the network that, hey, I just a little bit change it. So they are actually the same molecule.
So does that happen automatically, or do you do that by hand because you knew they were generated from the same original molecule?
It will be done automatically, but because we knew that.
I know you don't do it by hand,
Yeah.
but what I'm saying is when you just take your molecule, you do the modifications,
Yeah.
you run your graph neural network, you get 2 points for the 2 things in your latent space.
Yes.
So at that point, the 2 points may be far away.
Yes.
But since you knew they were near to each other, you sort of project onto comp hyperplane or something like that?
No, I mean, we use something called contrastive loss. I'll get into that. I mean, how we backpropagate and we adjust it. We train a network to learn that. So, and then you have another molecule, you do the augmentation, and these two things are not the same, so they repel each other. And all of this can be summarized in something what we call normalized temperature scale cross entropy loss, in which it is promoting it is a loss that defines as mentioned here, that it is causing these two things to attract each other, since the cosine similarity is 1. So that the Zi and Zj are these two molecules, and then it is locking them down to be the same. So we are forcing it to look the same. And these two things that are different, we force them to be different, you know, I mean, as a loss function, and we train using the contrastive loss. So we train a network. So this is our pre-training objective. And you can, we pre-train in that time on 10 million molecules, and we did this pre-training. And then we use this trained network to test it on molecular net benchmarks for quantum mechanics, for chemical, physical chemistry, biophysics, and physiology. And we showed with the vanilla, for example, graph convolutional neural network, or GIN, we showed that the pre-training significantly actually increases the accuracy. So you, especially, with the molecular, which is molecular contrastive learning, you can see, for example, for clean tox, we were able to increase the accuracy for classification, if it is toxic or not. Another data set is triple BP, which is the brain-blood barrier penetration. MUV, you can see, in that time, actually, we were moving the SOTA quite a bit, but now we don't work. Yes.
And why do you think, so the green bars are the best for all the other
Yeah.
data sets, but why do you think the gray barrier one doesn't perform as
I don't know. Yeah, I don't know why it's performing like that, but the majority of data sets, looking, for that specific data set, it seems that most of the methods are around the same things there. Except the N-gram. So for the regression tasks, like for example, predicting the solubility, we were not that much successful. So you can see that even we were worse in some of the cases. And you can assume that the reason is that so the labels in equations are continuous, and then you are perturbing the X or the feature space, then you're augmenting it. Obviously, the label also moves in the regression space. So yeah, for classification, you have a decision boundary, but for these things, you have a continuous spectrum of prediction. So that's why the model gets much more confused for the regression. We did ablation study to see that, okay, for example, to what extent you can perturb the molecule, or you can do which strategy for augmentation is better. So atom masking, bond deletion, subgraph removal. And we found out that, for example, subgraph removal, in some cases, in most cases, like to perturb 25% the molecule shows a better result. Okay, and then we saw these transformers coming into existence in the end of 2017, which, as most of you know, revolutionized the way that we model sequential data. And there's a gold sentence in the Attention is All You Need paper called, this paper solves the problem of sequential computing. That is completely true. I think with LSTMs or recurrent neural network, the idea of backpropagating in sequence was not a great idea, because obviously in one place, in one of these gradients, they become so small or so big, so they were not working very well. For example, if you wanted to classify the Shakespeare book, right? There are a lot of words. For each word, you need to backpropagate. It's quite obvious that one of them can be a small or big, so it will kill the signal of learning. But with the attention, you just remove all this backpropagation in time and solve the problem of sequential computing. And after that, Google gave the BERT paper, which is even better in terms of coupling the pre-training with the mask language model and the transformer, giving the P and T. These two technologies work with each other very well. So we saw a lot of interest in transformers. As soon as transformers came in 2021, we know that we have VIT, vision transformers, we had the mask autoencoders. People start building smart birds, and also ESM1 transformers. Some part of the AlphaFold actually works with that. And then we start thinking about how we can bring the transformers and pre-training together to two important areas of chemistry. One of them polymer, and another one metal organic framework. So I'll talk about the first one. which is for polymers. So in this paper that we published in 2023, we created a language description of polymers, especially for with enough capacity to parse different kind of polymer. If you have even two polymers or copolymers, if you have experimental conditions. So we created a kind of like token way of describing like the ratio, the type, the tag, for example, all these things. So we incorporated different kind of like locations for them. And the great things about the language or sentences is that you can just design it in a way that if you miss some part of the data, that's okay. So, you know, in shallow machine learning, one of the biggest challenges is that you have, if you miss one of the data, you should just remove the whole data, right? But in language, I mean, you can't have the language. So then we built a tokenizer, we tokenized this, and then we did the similar things as we did before in transpolymer, which we call it transpolymer. So it has a transformer for polymer, that you have a polymer sequence, and then you actually pre-train it. Similar to what we did, you can get a token, for example, with the mass language model. So, you know, in mass language model in BERT, you have two modes of pre-training. One of them is that you mask some places and then you run the dictionary over that, right? And you do the softmax, and then you predict that, right? And so that's a mass language model. So we use the mass language model for smalls of polymers. And then we had 1 million real polymer data. We augmented to 5 million. So you can do a small perturbation, and we pre-trained the network with 5 million, and then use that for fine-tuning, for property prediction. So the similar things is happening here, that you have a warmed up network, the weights are pre-trained, and then you take it here. But here, unlike the molecular paper, which we use pre-training with graph, here we are using pre-training with transformers. It's very similar to what is happening in BERT. So, and then what happened was that this striking results that we got that was very interesting. So before this, I was very interested in the polymers. And then when I was pitching the ideas about property prediction of polymers to companies like BASF or Covestro or Apple or wherever they do polymers, and they were asking always me, I mean, like, okay, how many data points you need for predicting, for example, thermal conductivity or band gap or dielectric constant? I said almost like 10,000. And they freaked out and they wouldn't contract us. But after, I mean, I got these results, you know, to them that we pre-trained a large, now they call it foundation model, but it was a very small model, which looks like a foundation model because it has a lot of pre-training. We were able to, even with a small data sets like 271 or 561 samples below like 1,000, we were able to predict the properties with good accuracy, you know, with good enough accuracy for the companies. And this was a striking result because for experimentalists in chemistry labs, for polymers, for metal organic frameworks, whatever you take, doing 10,000 experiments is a lot, but 200, 300, 500 is doable. So they really, like, I mean, we contracted like multiple polymer companies using our foundation models. And later on, we built actually much more bigger foundational models. So the one that we are working with these companies are right now around 500 million. So it's pretty big. And these results are much, much better thanks to the pre-training and transformers together. So this was one lesson. And one of the biggest things that I found out is what we call the knowledge gap. So when you are pre-training, this is actually the power of pre-training. So when we did this ablation study with 5K, when you pre-train, and then you have your label data, you see this value. So this is a gap in representation that you didn't learn. You increase it to 50K pre-training, you see that you have a better coverage in the latent space. So this is the latent representation. The gray one is the pre-trained data. The dots are the label data. And then when you do the 1 million pre-training, you can see almost you feel the knowledge. So that's why we have ChatGPT, right? I mean, the power of P is enormous in terms of like learning the whole representation. And then, I mean, you can use that representation to predict the problems.
You'd say we're learning something new, we're still in space.
Sorry?
Would you say we're learning anything new? We're still operating within space?
If it is out of this space?
No, if we're within this gray space, are
Mhm.
we learning anything new? You think?
No, it's just learning the representation. Yeah, because pre-training, the task of pre-training is just representation. As it is also in the language. In the language, when you are using mass language modeling, BERTs or similar ideas, you're just learning the grammar and vocabulary. Then the downstream task is solving an Olympiad problem, solving a math problem, question and answering. You give your paper, give me a summary. So that's downstream task. But like when you learn the language, I mean, you can do all of them. Just a little bit more push steps on the downstream tasks of the special thing. And this is similar to that. So this is like, I mean, pre-trained version is like a chemist who knows polymers very well, as opposed to a new freshman undergrad students in chemistry. So this is the second year chemistry student. This is the one. This is the one which got a PhD, but you hire him or her, and they say, hey, I mean, I wanted to get the thermoconductivity of this. Takes like 3 days for. But if you give that to the freshman, first you need to learn organic forms.
So wait, but when I train a PhD student, I do more than just have them rotate molecules and sort of take out
I
some
don't know.
clusters and so why are you saying that this kind of learning the representation is learning chemistry? It seems to me
It's much more about the undergrad or the bachelor degree. Yeah, I take it back about the PhD, but I'm saying that, I mean, like it's a general knowledge of chemistry. I said that this is the general knowledge of chemistry, that perhaps the fine tuning is a PhD or predicting the topic. Then, wow, I mean, like after that, I mean, we saw the power of pre-training in that work. So in 2023, we published this paper in JAX about MOFs, which, I mean, last week, many congratulations to all of you and also Professor Yagi for Nobel Prize. So in 2022, actually, my 3 PhD students who are here, actually, it's very interesting. NVIDIA, Apple, so 3 of them who just got into the industries like that. We used the transformers for metal organic frameworks for the crystal structures, and then we created something like MOF ID representation, which is the language like, and then we used the transformers to encode that. So that's one encoder. And then the way that we created a MOF ID was that these beautiful frameworks, we created a way of just encoding it into a language representation. So, for example, for the topology, we have a specific code. In that time, for the format, we have a signature for the organic building. And then we were parsing this as a kind of language of MOFs. And then what we did is what we call multimodal pre-training. So you know that everyone is using CGCNN, the crystal graph neural network for crystals, so you can encode it. You have an embedding, you take it to the latent space. Then you have this language one, you can use a transformer, you can encode it, you can take a latent space, you can take it to the latent space, and then you can multiply these two together and create something called cross-correlation matrix, right? And obviously, like, I mean, if you have a cat, a picture of a cat, and then you write cat, so cat is the language of representation of that image, and the sound meow, right, is the voice or sound representation. So you have 3 modes of data representing cat, and here is the same. So you have one way of representing metal organic framework, we have a language version of predicting them. And these two things are the same, right? I mean, cat is a cat, right? I mean, sometimes you hear its sound, you say it's a cat, and also sometimes you see it's written, it's a cat, it's a cat. So in the latent space, when you multiply this cross correlation matrix, obviously the diagonal of this matrix should be identical. Why? Because these are the multiplication of the same entity of the crystals to the language version of that, and then you should create a back propagation system in which you wash out the off diagonals and the identity be one.
So is that just a rotation of a basis, the last error?
Yes. Yeah. And then what you do after training is done, you will see that the off diagonal elements of this matrix are washed out, and then you can see the diagonal one is sparkling somehow. I have a figure later on I'll show you. And this means that you train the true encoder. So you pre-trained a CGCNN encoder, you pre-trained the transformer encoder. And then the interesting question is that, okay, so what? I mean, right, what's the benefit of doing this? So the benefit of doing this is actually learning from two modes, right? I mean, so we wanted to see that if the language encoder is infusing more knowledge to the crystal representation or vice versa. That's an interesting. So we wanted to see if there is a synergistic learning, right? I mean, synergistic learning between these two things. And then actually we did some studies on the famous MAP data set. There is HMAP and QMAP. And we saw that the transformer pre-trained, I mean, you can see the error is reducing to a good extent, when you are doing the pre-training. Another interesting thing that we found out is that whenever you're using each of these branches separately, but you pre-training and you eject, each branches, when they are pre-trained with actually infusion of the knowledge, this encoder's performance is much, much better compared to the time that you start from scratch. So it seems that you inject the data or information from another mode to another mode's encode.
So when you say data, what is your data in? Is that DFT data?
These are DFT data, yeah.
Not experimental data.
They are not experimental. These three data sets, they are DFT data. And then recently, actually, yes.
So how does this compare to, say, the ground truth? So what's the ground truth?
These are all errors. So whatever you see on the bar is actually the difference to the ground truth.
Right, but the ground truth is DFT ground truth.
So DFT. And also recently, like a few weeks ago, we created another paper that I didn't put a lot of updates, but since this is the MAF time, we call it MAF GPT, which is the generative design of metal organic frameworks using language models. And actually here we use the MAF format that we have, and we've used the reinforcement learning, and we created a combined reward function in which actually it is boosting the generative design of a metal organic framework, and it checks the validity, novelty, target, and diversity. So I just brought this one single slide that we did this also interesting work. I mean, I don't, in the interest of time, I don't go to the details, but this is like a GPT model that we pre-trained on a lot of MAP IDs, and then we are able to, with the RL tuning, actually generate some MAPs. So in the second part of my talk, I'm going to go and talk about a little bit about catalysis and the efforts that we did through these three works that we did. The first work that is talking about is the full migration from graph to full text. So I wanted to just to tell you that how effective is the textual description. The second one is, which again published in Nature Machine Intelligence last year, is the integration of the graph neural networks with the language models in the multimodal learning. And the last one is agents, which actually full usage of the agents. So there are challenges. I mean, like graph representations are really good representations for molecules, but there are challenges. For example, some of these graphs that we are making, sometimes it's indistinguishable, in terms of property prediction. We have inductive biases such as equivariance, like translation, permutation, and rotation. And also, you definitely need a structure, right? So you need a structure to define it with a graph. And also there is limitation in terms of unstructured loading of the features. So
May I ask a question on this translation, permutation, and rotation?
Yeah.
Because that astonished me a little bit, because when you started very early on, you said you have a data set of dogs and cats, you don't know what they are, but you know that when you rotated if it was a cat before, it's one afterwards. So why doesn't this work here?
it works here, but there is a level of how it works here. Like, I mean, the level, I mean, we wanted to see that if there are better encoders. So that part of pre-training is still fixed here. I mean, like we are going to use that type of rotations, but the question is that is the graph neural networks for representing a molecule is 100% the answer to the representation of a molecule or not? So that's what we are trying to talk about. And the idea that when I was talking to my students who became a professor now, Jang-Woon, I told him that, okay, if you take water, for example, it has hydrogen, and oxygen. And then when you are just loading it via graph, you have 2 bonds, right? And you have 3 nodes. But in terms of text, how many books we have about water? 2,000, 3,000, 10,000. We have large amounts of data that even we are not able to use that beneficially for representing water. Geometrically, we can actually represent water in a nice way. I mean, define the angle, right, and these things. But I mean, for example, the information like the water covers 71% of the Earth's surface. Perhaps we can load it on hydrogen or oxygen, but that looks a little bit awkward to me. So because of that, I mean, I had this idea which I just wanted to try as a professor, like can we make accurate prediction without relying on atomic structure? Consider that you don't have atomic structure. You have a system like this, you have a catalyst, you have the substrate, you have, for example, adsorbate, and then you have this system, right? I mean, you don't want to use graph. What do you do? Like, how do you represent if you want to use language? Any idea? Very good.
Yeah,
What else?
general binding distance, electronegativity.
Very good. Yeah.
Yeah.
Actually, you can measure the distance and say, okay, the distance between, for example, the oxygen here and the first atom is like this much, the shortest distance.
Picture is worth 1,000 words, as they say, right?
The picture. Also, I mean, remember that, I mean, we never used pictures for molecules. So it was like an interesting idea. So the first thing that we did, we wrote a script that we decomposed the system into textual string NO. I mean, this is the adsorbate molecule. Then we talked about the surface. We talked about whatever we see here in an automated way. And then we parse every parse to a different tool. For example, we send this first one to the ChatGPT, and it said the NO molecule characteristic. This molecule has a linear geometry with a bond angle of 180. Then they use a surface type of titanium palladium, surface 100. It talks about it. And then as you mentioned, like there are things like which are created here in any material initiative, robocrystallographer, right? Robocrystallographer talks about
for example, the structures. And then we in a kind of like automated scripting, we bundle the prescription, right? And we bundle everything. And then guess what? I mean, you can use obviously a pre-trained language model, right? I mean, in that time, I think in 2023, we had this Roberto and Alberto, lightweight, language model, and just you create a text and you make a learnable model, then obviously you can use the pre-trained Roberto or Alberto and go directly to energy. So previously you used the graph to go to the energy, now you use the text to go to the energy. You have a regression head module, and then you can train, fine-tune it for the energy. You have the data set, but this is the way that you can use, and here you can put Roberto, Alberto, Bert, whatever you like, right? We did this. It was very interesting, actually, a study that we did about like engineering the feature space. Like, I mean, what is the best way to, create a structure into text that you can do ablation study? Should you have the secondary interacting atom, for example, primary interacting atom? And then we see, and we call it cat-berta. So it's catalysis berta. So we call it cat-berta. In our GitHub page also, there's a cat which is making experiments in chemistry. And it was interesting. I mean, like the results were to some extent on par with the graph neural networks, but not still similar. Like, I mean, we're a little bit underperforming. But as you can see, the results are not that much bad, like R squared for the test set. So another big benefit that we could see is the attention heads, right? I mean, you can use the attention heads, you can visualize them, and you can see what are these attention heads are sparkling or showing. So for example, we saw a cluster of like adsorb NH3, you can see is very important, bridge, like this coordination, right, a number. So self-attention scores give you interpretability as opposed to graph neural networks, which almost, they don't have that much predictability. So we did a lot of different kind of studies, which I skip. And then we wanted to increase the accuracy of this even more to predict much more accurate. How can we improve prediction accuracy when using textual input? And then what we did is that thinking of like how, for example, you can incorporate multimodal data. So you have, for materials, you have microscopy, you have a spectroscopy, composition, synthesis protocol, and then you have all these data that is different modes. For example, a spectroscopy is image, for example, of a figure or CSV data. Composition is a kind of like data. Synthesis protocol is text, right? And the question is that can we co-learn together? And we did similar things that we did in Morphomer, in metal organic frameworks. We thought that, okay, we merge or marry the two best words, so the graph word and the text word. So we know that the graphs are able to distinguish structural nuances, high accuracy, but the requirement for atomic structure, and they are high inductive biases. But text, human readable, easy feature incorporation, you can do a lot, but not able to discern structural nuances and relatively lower accuracy, so which we had. So in order to do that, we did, as I mentioned, similar things in this paper, that we did this cross-correlation matrix, or what meta people call it. Anyone knows what is this called? This type of learning, it starts with a C. CLIP, right? I mean, contrastive learning of image. Yeah. So pre-training, contrastive learning of image pre-training. So in this way, what we did for the pre-training, we created a graph version and we freeze the graph encoder. So, I mean, it can be crystal graph convolution. We encode it here, and these are all without labels. So we don't care what is the energy or whatever. We just talk about the structure. We put text, we created a language model encoder. We had the projection here, and then we created this, cross correlation matrix. And again, I mean, back propagated. We didn't back propagate to the graph neural network, but we back propagated to the language model encoder. We wanted to fuse the data of the structure into this encoder to make it actually structuring.
So what does the diagonal there mean? The two spaces are not necessarily the same dimension.
Since you take it to the latent space, you define
In the same
in the same
dimension space.
intentional. Yeah. We put it into the same dimension, and then the diagonal, because this is the same text for the same graph, so it should be 1, right? The cosine similarity is 1, and the off diagonal. Yeah, so that's the training objective, maximize the similarity between correct graph text pair while minimizing it for incorrect pairs. And then this is what is happening. So this is the initialization, I mean, like at the beginning of the training. So you see this matrix. And after you train, you see this the sparkling diagonal. And then we plotted actually the latent space after the pre-training is done. You can see that it learns that these two things, and the other ones are after multimodal training. So after, so it's very interesting that you, for the data that you had, the graph ones, we freeze this. So we didn't actually pre-train at the same time both the structure encoder and the graph.
Can you show back the previous? Can you clarify, like, it's clear that the diagonal is one part, but there seems to be a lot of off-diagonal structure of, at least visually, a very similar order of magnitude.
Yes.
It doesn't seem to be very small. It doesn't seem like the off-diagonal structure is that small.
Yeah, so that's the stability of training of multimodal. It's very difficult. We had a lot of challenges even getting this. One of the biggest problems. So if our initial goal was actually to pre-train also graph as well, so to back propagate into that branch, but we stopped doing that. We just encoded it to the latent, and then the back propagation goes through this branch. But still with that, you could see what we got. It was terrible when we released both of them.
But what's the implication of that? Because that, intuitively, it seems to me like that means that these two projections are basically have, even though there is a strong kind of recognition of where they match, they also have very significant projections in other dimensions, which means that at inference time, the mixing of those is going to be very significant.
Yes, let's see the inference statistics. Yeah, it performs better. Still, it performs better. So, like when you pre-train this one using this data, still it's better than starting it from scratch.
So you said releasing those didn't work. What if you do what people do in many clustering algorithms, or so that you first sort of backpropagate the language model, then you freeze that, and now you backpropagate to the graph.
It did that. It didn't work as well.
It didn't work.
Like for example, GANs. I mean, that time that we worked, nobody is working with GANs now with diffusion, but in this one we created the discriminator a little bit and then generator. No, I mean, we tried that didn't work. I mean, those are also very interesting points for the study, but the training was unstable for this one. So and then you can use this encoder, which is pre-trained for inference. During the fine-tuning, you can attach a regression head and you can predict the fine-tuning for energy. And this is the result. So the results are like showing that. So the benchmark is this one is without multimodal training on the language part. I mean, we don't forget about the graph on the fine-tuning. Then with the multimodal training, so we have 9.8% decrease on OC20 data sets on the meta data set for the large. And like OC20 has different levels of data. So we have large and a small plus OC20 dense, and also pre-training on OC20, fine-tuning on OC20 dense. So we see almost like between 5 to 10% enhancement. So we should worth it actually to do that. But I totally agree with you. I mean, we couldn't wash out, I call it wash out of diagnosis. But also the parity plus R squared without multimodal is 70%. With multimodal is 88%. So it's a better actually harnessing of standard deviation. Also, we looked at redirection of the head. So also it's changing. It's very interesting that when you are using the graph, the heads that are attending to the adsorbed catalyst, you are also changing their behavior. Okay, so the last part that I'm going to talk about is this agent design. So consider that you wanted to have a kind of large language model or any kind of algorithm to find the configuration enumeration or find out the minimum energy sites on a catalyst, and you have your adsorbate. So in order to do that, usually you make some guesses, right? I mean, you want to do that as soon as possible. You make some guesses, you put the adsorbate there with different configurations, right? And you calculate the energy using DFT, and then you find the site, right? I mean, you go to the next site, you guess. But the question we are thinking about is that there are a lot of steps you should try, right? I mean, to find out. So we wanted to see that if large language models like ChatGPT or Claude or Gemini, are they capable of like getting all these scenarios and plan the next location / configuration that you should put your catalyst to lead to the minimum energy? So that's the question that was very interesting. And the search space, what they call it, the search space reduction, as experimentalists, most of you or some of you are experimentalists perhaps, you try to do it via design of experiment, right? You do the Bayesian optimization, or you do experiment 1, you do experiment 2, what's the third one I should do to reach the property that I want, right? So we wanted to see if that is possible with the LLMs to reach that. So can we reduce the configuration circuit space? Can we automate this process to enable large scale applications, right? Also, you wanted to do the automation, right? I mean, you wanted to do everything in automated span. And then you can have an LLM that you do chain of thoughts or few shot learning and do that. How we did that, we created a few agents. So the input query is derive the most stable configuration of adsorbate and catalytic surface system. So we created an LLM module, which is a solution planner, and also another LLM module, which is the critic. Then its output create a solution. So what are the site types? Surface binding atom, adsorbate binding atom, adsorbate orientation. Then there is another LLM module, which is giving out the binding index. So assign 1 to the surface bound atoms, 0 otherwise. And then we reconstruct the structure. So based on that idea of that it is proposing, we convert the language into configuration, and we retrieve. So we have program tool that retrieve the structure. We create the initial structure that the LLM tells us. Then there is, I mean, you can use the equiformer version 2 or 3 for the GNM relaxation, because you need to do the relaxation. And then we have another program tool which does the anomaly filter, and you get the relaxed configuration, the minimum of what is the relaxed configuration. So this is the whole pipeline that an agent can do. For example, the solution example is that the system, you have NNH, then CUPD3, the material ID, and the solution is the site type, hollow side atoms, atoms. So you can just actually write all this, and then you can make a binding indexer, like about like how you go back and forth between a structure and language. So we run it on the three famous reactions: nitrogen reduction, hydrogen reductions, and oxygen reduction. And you know, all of you are familiar with these volcano curves. And we wanted to see that how we are doing on different kind of catalyst systems that we have. And then the goal is to find the most stable configuration with reduced number of initial configurations. So one example is NNH CuPD3. The bridge site obviously is Cu and PD, and the site orientation NN. So if you do the enumeration with the heuristics methods, you need to have 78 steps. And the absorption energy, the minimum absorption energy that you find is 4.95. While if you do it with the AI agent, the initial configuration is only 20, and you even get to the much more lower energy. So I just wanted to show you the holistic plots that we have here. So the pink ones are all the enumerations that you need to do. But with the AI agent, you can see that a smaller number of tries we did, and then it was able to actually find out this lower minimum energy. That is, so we calculated the success ratio and lower energy determinations, capability to predict the absorption energies and capability. So we created two metrics. One of them is to match the algorithmic approach that predicting absorption energy, how many times you are successful and how many times you are able to find out lower energy compared to the heuristics. We found out that it's actually the number is with 27% of the original initial sets, 17 out of 20 match the ground truth, 7 find even lower energy. So that's the statistics we got out of this. And then it is also performing, the great thing about these agents is that if you give a monometallic system or intermetallic or a small adsorbent or large adsorbent, it's actually performing better. Also across different kind of language models. So GPT-4o, DeepSeek, Cloud, and GPT-4o Mini, you can see that the lower energies that are predicting, how do they look like compared to the SR. So you can see that, for example, GPT-4o Mini does pretty much good performance if you want to compare the different models. I think I'm almost done. There are too much more developments that we did in the lab. This paper that just got accepted is also about agents. And I think, that's the vision that I see for material discovery, that we will have, for example, this is a computational agent that goes, you give a prompt that I wanted an energy, I wanted to find a material with this amount of band gap. So it goes and we create for example, material retrieving agent that it is calling, for example, some deep learning model like crystal LLM to create the crystals. Then it sends an automatic molecular dynamic or DFT calculations, send back the data to the agent. Then for the continuum simulation, it launches the grain boundaries. And this is an interesting paper that we did, like there are 20 examples of different kind of like material discovery in them. Another paper that is about to appear is for drug discovery. So for example, you wanted to find out, you give a prompt that you wanted this drug for cancer, leukemia cancer. It goes and extracts the, so there's an agent that goes, extracts the data. There is a kind of like database of SMILES that you use it as a seed molecule. Then there are arrays of deep learning models that the agent calls for affinity prediction, absorption, distribution, metabolism, excretion, and toxicity. But the heart of this, which is very interesting, is this molecular refinement. So at each time that, for example, you need a binding affinity of 5.8, but this molecule that the agent suggests is 4.5. So the agent is going to go and change the molecular composition, like add a carbon, add a nitrogen. So this is called molecular refinement. It's like a medicinal chemist. And then again, send it back to the property prediction because you may have other properties, like you may make it toxic now. And then it does the structure generation, and then it does this loop till it reaches the prompt goals that you have. Okay, that's the end of my talk. Thank you so much. We are a big lab. Always excited to hire. And actually, Kevin Hahn, he was working, some of you may know him, he was working with Cedar. He's now a PhD student in my lab from computer science at Berkeley, who is working on chemical synthesis. So we think that the chemical synthesis with LLM is a holy grail that we need to solve, and I spent a lot of money there to do that. Thanks so much. Okay.
Running out of time, so we will skip the Q&A question. But the professor will be around this afternoon, so if you have questions.